In August of 2024, a research team at Northwestern University published a paper that quietly redrew the boundaries of what construction could be. They didn't announce a breakthrough chemical, they didn't patent a new synthetic material, they took ordinary beach sand, soaked it in seawater, passed a gentle electrical current through it. Somewhere between 2 and 4 volts, less than what powers and double a battery, and watched loose grains lock into a solid rock-hard mass within minutes. No cement, no mixing, no kiln fired to 1400 degrees Celsius. Just electricity, sand, and the ocean. Professor Alessandro Rotoloria, who led the study, described those first lab experiments the way someone describes watching the impossible unfold in slow motion. The sand didn't simply harden, it became something different altogether, dense, cohesive, structurally sound, not manufactured, not fabricated, grown from the minerals already, dissolved in seawater itself. The paper landed in Communications Earth and Environment, a journal inside the Nature portfolio. Peer-reviewed, independently verified, confirmed by mineralogists. The science held, and then, the way so much genuinely important science does, it slipped quietly into the archive while the world kept buying bags of Portland cement at $30 a pop. This is where the story starts, not with conspiracy, with a question that deserves a real answer. When a process this significant lands in one of the world's most respected scientific journals, backed by the Army Research Office, verified by physicists and engineers, why does almost nobody building infrastructure today know it exists? The answer requires going back to 1976, to a German-born architect named Wolf Hilbertz, standing underwater off the coast of Texas, a mild electrical current running through a metal frame he had built with his own hands. Hilbertz wasn't a chemist. He was trained in architecture, which is perhaps exactly why he came at the problem the way he did. He was consumed by a single question most engineers had never thought to ask: how does a coral reef build itself? A coral reef is structurally harder than most commercial concrete. It grows in the harshest saltwater environments on the planet. It repairs itself, strengthens with age, and builds itself from nothing but seawater and electricity generated by living organisms. Hilbertz thought, what if you didn't need the organism? What if you could replicate the chemistry with a simple electrode and a low-voltage current? He ran the experiment, 2 metal electrodes in seawater, connected to a low-voltage DC source. What happened next had never been documented outside of biological systems. Calcium carbonate, magnesium hydroxide, hydromagnesite, minerals dissolved in the seawater began precipitating out of solution and depositing directly onto the cathode, layer by layer, crystal by crystal, building a dense, solid, load-bearing structure from water. He called it mineral accretion. The world would come to know it as Biorock. By 1979, Hilbertz had published in the IEEE Journal of Oceanic Engineering. By 1981, the U.S. Patent Office had issued him a patent for large-scale structural mineral accretion. The compressive strength of the material measured between 3,200 and 5,350 pounds per square inch, comparable to concrete used in sidewalks and low-rise foundations. It required no extraction, no mining, no combustion, and no factory. Hilbertz spent the rest of his life building artificial reefs across more than 40 countries. When he died in 2007, more than 500 Biorock structures existed worldwide. His work was exhibited at the Museum of Modern Art. The scientific community acknowledged his contribution. The construction industry ignored every word of it for nearly 5 decades. To understand why that matters, you need to understand what we're currently doing with cement and what we're paying for it in money, in carbon, and in coastline. The global cement market exceeded $47 billion in 2024. The broader concrete and construction materials industry eclipses $1.8 trillion when you fold. In ready-mix, precast, and structural applications. We pour more concrete every 3 years than was poured across the entire 20th century combined, and the cost no quarterly earnings call leads with. The cement industry is responsible for roughly 8% of total global CO2 emissions every year, the 3rd largest source of hard-to-eliminate carbon on the planet. Producing 1 ton of cement releases approximately 900 kilograms of CO2. That release isn't an inefficiency engineers just haven't gotten around to solving. It is inherent to the chemistry. You cannot make Portland cement without decomposing limestone at extreme heat. There is no carbon-neutral version. It is chemically impossible under current processes. When climate targets demand a 16% reduction in cement emissions by 2030, the industry responds with carbon capture proposals and incremental efficiency upgrades, all of which cost money, none of which change the fundamental chemistry that has been releasing carbon since the 1820s. Meanwhile, Rotoloria's team ran the numbers. The cost to cement 1 cubic meter of marine sand using electrodeposition, $3 to $6. Conventional binders for comparable coastal applications, up to $70 for the same volume. That is not a marginal improvement. That is an order of magnitude cost reduction with 0 carbon emissions, no mining, and no proprietary compounds. just electrons and minerals the ocean already provides for free. The mechanism is worth understanding because it is one of the most elegant pieces of applied electrochemistry in recent engineering literature. Seawater is not just water. It is an electrolyte loaded with dissolved ions, calcium, magnesium, bicarbonate, chloride, sulfate, the same building blocks every coral and shellfish uses to construct its skeleton. The chemistry is already in the water. What is missing is the energy to drive precipitation. When current flows between two submerged electrodes, it raises the pH at the cathode. Calcium carbonate loses its solubility and precipitates directly onto the electrode's surface and onto any surrounding sand. The mineral crystals don't just coat the grains, they grow bridges between them, interlocking across the void spaces and cementing the entire matrix into a coherent solid. At 2 to 3 volts, the dominant deposit is calcium carbonate, the same mineral forming the Great Barrier Reef. At around 4 volts, the reaction shifts toward magnesium hydroxide and hydromagnesite. Rotaloria's team was the first to document hydromagnesite forming through this process. The resulting material reaches compressive strengths of several megapascals with hydraulic conductivity reduced by an order of magnitude. The team also showed the entire process is reversible. Flip the polarity and the minerals dissolve back into solution. The rock becomes sand again. A material process you can undo on command suggests programmable ground infrastructure, modifiable, repairable, removable without demolition equipment and without generating the 1.3 billion tons of construction waste the global building sector produces every year. And Rotaloria's team isn't working alone. A parallel field called biosmentation has spent 2 decades developing an equally radical approach using microbiology instead of electricity. Microbially induced carbonate precipitation introduces a specific bacterium into sand alongside urea and calcium chloride. The bacterium produces an enzyme that drives a reaction forming calcium carbonate crystals directly at the contact points between grains, fusing them together. In a landmark field test, researchers grew a 100 cubic meter sand column, 2 strengths up to 12 megapascals, stronger than some architectural concrete at ambient temperature with no combustion and no emissions. What ties all of these threads together? Hilbertz in 1976, Northwestern in 2024, biosmentation. Researchers in between is the same logic. Nature already knows how to turn loose granular material into solid stone. The scientific challenge was never whether the chemistry was possible. It was whether humans could drive it on a human timescale without extreme temperature, pressure, or millions of years. The answer is yes, with a few volts and the right electrode. The concrete and cement industry is not the villain in a simple story. It built the tunnels, the bridges, the water treatment plants that keep cities alive. But the 8% of global CO2 it generates, the billions spent on coastal barriers that erode and fail, the mountains of inert demolition waste. Those costs are now being weighed against a process that requires no new chemistry, produces no combustion emissions, costs $3 to $6 per cubic meter, and can be undone. According to the European Commission's Joint Research Center, nearly 26% of the Earth's beaches will disappear before the end of this century. More than 40% of the global population lives in coastal zones threatened by sea level rise and erosion. The conventional response is seawalls costing millions per mile, structures that erode, leach chemicals into marine ecosystems, and fail catastrophically when the sand beneath them liquefies under storm surge. Rotaloria's process runs on a floating solar panel, no toxic byproducts, and it can be reversed if a community changes its mind about where it wants its shoreline to be. No other coastal protection technology in existence offers anything close to that. The Biorock reefs Hilbertz built in places like Pemuteran, Bali, now among the most celebrated reef restoration projects on Earth, have stood for over 2 decades. Built for less than the cost of a single section of conventional seawall, growing stronger every year, hosting thousands of species, built by an architect who looked at a coral reef and asked one question the entire construction industry had never taken seriously. What if the ocean already contains everything you need?